Hello friends, in this video we're going to discuss about damped harmonic oscillator and differential equation for damped harmonic oscillation and general solution and frequency of damped harmonic oscillator. Before we start, please do subscribe the channel, hit that thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. That's my Insta ID, so you can follow me on Insta. Okay, so now let's start. So now damped harmonic oscillator. Okay, suppose when a body oscillates in a medium, then the medium offers a resistance to its motion of the oscillating body. Okay, as a result, the amplitude of the oscillation goes on decreasing due to the resistance provided by the medium, and ultimately it becomes zero. Okay, this type of motion is known as damped harmonic motion, and the system, this oscillating system, is known as damped harmonic oscillator, right? So that means, let me explain. Suppose we have a system. So this is a spring attached to the rigid wall. One end is attached to the rigid wall, and here we have a horizontal plane, and we have a block here of mass, suppose m. Okay, now you see this mass is at now mean position, at equilibrium position. Now if you pull this towards this direction and if you release it, then it will start vibrating like this, it will start oscillating like this. But in its oscillation, due to the friction between the plane and contact surfaces of the block and this horizontal plane, so in its oscillation, the amplitude means the maximum displacement from the mean position towards the extreme point, that is amplitude. So in first oscillation, suppose from this point it reaches this point, suppose in the next oscillation it will reach, it will cover very less, it will cover less distance. Okay, it will undergo less displacement. Okay, compared to the first oscillation. In second oscillation, okay, and it in suppose this is the point to which it reaches in first oscillation. In the next oscillation it will reach to this point, in the next it will reach this point. Okay, similarly this amplitude will goes on decreasing in its oscillation, right? So hope you have understood this. This kind of oscillation is damped harmonic oscillation, right? Because of the friction, so this is oscillating like this, it is going this way towards right and left. In the second time its amplitude will be decreasing like this. In this third time, so here is the amplitude in the first time, amplitude in the second time, in the third time. Okay, so hope you have understood this way this amplitude will goes on decreasing, and there a time will come when this amplitude will be zero. Okay, that means this oscillation die out. Okay, so now you see, so let me go to the next page. Okay, to obtain the differential equation, let us consider this spring mass system. Okay, so one end is attached to the wall and another end is attached to a mass block of mass m. Suppose we have a spring mass system. Okay, spring mass system as shown in the figure. Okay, mass of this block is m and it is at x is equal to 0. Suppose this is the mean position and it is pulled to the position x. Okay, so it will start vibrating. Okay, so now you see, when it is pulled towards right, the spring will pull towards left, and when it is pulled towards right, then friction will come into play in opposite direction. This pulled in this direction towards positive x-axis, then friction will act in the negative x direction, right? Okay, then restoring force of the spring, we know that formula to calculate the restoring force is minus k x. K is the spring constant, right? And the kinetic friction between the block and the surface is directly proportional to the velocity. We know velocity is given by time derivative of position dx dt, or x dot we can write, okay? And if this kinetic friction is directly proportional to velocity, then if to write equal sign we need a constant, okay? And that constant be suppose b. So just give me a second. So here we can write kinetic friction Fk is equal to minus b dx dt, time derivative of x, okay? And here you see this is nothing but velocity, this is velocity, okay? And b is the constant of proportion, constant of proportionality, right? So then net force acting on this block will be given by this frictional force and kinetic friction, okay? And here you see, just give me a second, sorry, just give me a second, just wait. So here you see, okay, so kinetic friction Fk, that is minus b, negative sign, as you see this is acting in opposite direction of the displacement, that's why negative sign should be given, okay? Derivative of x with respect to time t, it gives velocity dx by dt, this gives velocity, right? So minus b is constant of proportionality, right? So now you see, so let us put the value of Fr, frictional force, and the kinetic force, okay, right? And now you see the net force according to the Newton's second law of motion. The net force is given by mass into acceleration. If we consider the mass of the block is m and acceleration is a, then ma, and acceleration is given by this expression, acceleration a is equal to second order derivative of x with respect to time t, right? Hope you know these things. We know that acceleration a is equal to second order derivative of x with respect to time t, right? So that is what we get, okay? Now that's why we can write this. So this is, just give me a second, wait, let me write it properly. So sorry. So now you see net force will be equal to m second order derivative of x with respect to time t, d2x dt2, okay? So this is mass into acceleration. So now you see here, so in the above expression we have got net force is equal to this, and according to second law we have got this is the net force acting on the block. So we can write this is equal to this, right? So let me write on the next slide, okay? So let me write the two expression of net forces. So we have got these two, right? Now therefore we can write that mass into acceleration is equal to minus kx minus b dx dt. Okay, so let me simplify this equation. Okay, this can be simplified in this way, right? And let us divide both sides by m. Okay, so on dividing the equation both sides by m, we have got this. Now here you see, let b by m is supposed twice beta. So for simplicity we have taken twice beta. That means we have considered beta is such a constant. If we multiply it by 2, it gives b by m. That's it. Okay, and suppose here k by m is omega naught square. So when you say, when there is no frictional force, if you consider the harmonic oscillation, in that case frequency is given by, which is omega naught is equal to k by m. Now here the frequency of damping oscillator will be different. Okay, so here k by m, not only k by frequency will be not given by k by m in this case. Okay, so k by m is the frequency in case of a oscillation harmonic oscillation, when there is no any friction and any resistance. Okay, right? So beta will be equal to b by twice m, right? Okay, this is called the damping parameter. This is called damping parameter. Okay, so now you see, if that is the case, we have considered these things. So this above equation can be written this way: second order derivative of x with respect to time t, plus instead of b by m we're going to write 2 beta, first order derivative of x with respect to time t, and k by m we're going to write omega naught square x is equal to 0. So here we have got this differential equation. Okay, so this is equation number 1, and this is the differential equation for damped harmonic oscillation. Okay, right? Now let us solve this. Now you see, I'm going to solve this differential equation as we have learned in mathematics or in mathematical physics, but in different books, in the books of mechanics, in classical mechanics, in different books you will get generally a solution of this kind of equations are assumed. This can be of this form, but I'm going to follow the method that we have applied in mathematical physics. Okay, so first let me obtain the auxiliary equation first. So here you see this equation number 1. Here you see, let me copy this equation. This equation number 1 here, it can be written this way: d square plus 2 beta d plus omega naught square d, sorry, here into x, that's supposed to be x, is equal to 0. That means here you see, d square means this second order differential coefficient, and d means the first order differential coefficient. Instead of d by dt we have written capital D, right? Hope you have understood this. And the x, this x is taken outside. That's how we can write this equation, and from here we can write the auxiliary equation, right? So let me go to the next slide. So let me show you. So let me write the equation that we have got first. This was the equation that we have got. Okay, so it can be written in this way, right? Therefore the auxiliary equation can be written in terms of, sorry, okay, so here I have considered p square, 2p plus omega naught. P is a variable, and this is nothing but a quadratic equation, and this is known as auxiliary equation here in this case. So let us solve this. If we apply the quadratic formula, we can solve this way, right? Here you see, if you compare with ax square plus bx plus c is equal to 0 with this quadratic equation. And if you apply the formula that x is equal to minus b plus minus root over b square minus 4ac divided by twice a, then you will get this result, right? Here a is equal to 1, b is equal to this twice beta, okay, and c is equal to omega naught square. So that's what we have got, right? Hope you have understood this. Now you see here when if you see in most of the books, when we write auxiliary equation, we used to write in terms of n instead of p, but here I have considered small m as a mass, so that's why I am writing here p. Okay, so now here the roots will be p1. So here you see you can take 2 common and square root of you can take 4 common and square root of 4, that will be 2, and then again you can take 2 common, which will be cancelled by these 2. Okay, hope you have understood this. That means this way, minus 2 beta plus minus root over 2 root over b square minus omega naught square. Okay, this 4 is taken common and square root of 4 is 2. Okay, then this 2 is also taken common, then we will get this equation. Then this 2 cancel. So here we have 2 solutions. Here we have minus and plus both. So that's why, so the 2 roots will be equal to minus beta. First let me write plus root over beta minus omega naught square. Next divided by 2. This is cancel out, right? 2 is gone now. So this is one root, and another root, let it be p2. Let me write the other root as p2. That will be equal to minus beta minus root over beta square minus omega naught square. That's what we will get. So we know, you see, in case of differential equation, that differential equation of this form that you have solved in mathematical physics like this, d square, suppose you have any constant, suppose a, b, c, something, whatever it is, okay, b suppose d plus suppose c, x is equal to 0. When we get this kind of equation, we used to write the auxiliary equation like this, plus m square plus bm plus c is equal to 0. This was the auxiliary equation. We used to write this, and we used to write the roots m1 and m2. Here I am writing, instead of m1 and m2, p1 and p2. Okay, and solution is given by solution of this equation. If this is x, then it is given by x is equal to cf plus pi. Okay, so cf means complementary function, pi means particular integral, and here on the right hand side we have 0, so particular integral will be 0, and we end up getting the solution cf. Okay, x is equal to cf, and cf in this case, if we get m1 and m2 as roots of this auxiliary equation, then we used to write the solution this way. We used to write two constants, c1 e to the power m1x, okay, plus, right, sorry, not x here, okay, in this case we have this x is function of t. We are differentiating with respect to t here, so here we have to write t, okay, m1t plus c2 is equal to e to the power m2 t, and it may take different forms depending on the nature of this m1 and m2. Okay, so here instead of m1 and m2 we have p1 and p2. Okay, we have p1 and p2. Okay, we have p1 and p2. You don't need to write these things, okay, that I have written in written on this side. Okay, just I have written those things to explain, okay, the matter. So therefore here, as the particular integral is 0 on, because we have right hand side is equal to 0, so cf is the solution here. So So therefore in this case our solution will be x equal to, which is a function of t, so we can write x of t, which is equal to c1, which is any arbitrary constant, that's going to be equal to e to the power p1 into t plus c2 e to the power p2 into t, right? So we're going to use these two values instead of p1 and p2, right? We're going to use these values, we're going to use these results. Hope you have understood this. Okay, so now you see, okay, let me take a new slide. Okay, so let me write the roots first. These are the two roots here we have got, and putting these values here in this solution, it will take of this form. Okay, so p1 and p2 are replaced by their values, okay, that we have got here. Okay, so this is the solution, this is the general solution. We can take, you know, t to the power e to the power minus beta into t from these two terms. Okay, so this is taken common, I am taking common, we have got this expression. Okay, so hope you have understood how we have taken common this. So now you see, in this case this can be written this way, e to the power minus beta t, then plus root over b square minus omega naught square into t. Similarly here we have plus, so that's why we can write this way, product of these two. Okay, so using the laws of index, again you will get, if you multiply this, then again you will get this, right? Hope you know these things. Then similarly this can be written this way, e to the power minus beta t minus, so here into e to the power minus root over beta square minus omega naught into t. So here this one is taken common, right? Hope you have understood this. So on taking common, we have got this expression, right? So this is the general solution, this is the general solution of the equation number 1. That means of the differential equation that we have got for the damped oscillation. We have got the general solution of this equation. Okay, so this is the general solution of equation number 1. So now let me take a new slide. Now here you see this part represents the oscillating, you know, function. Actually it shows how, you know, oscillation takes place. Okay, this represents the oscillating term, and this part you know, shows how this amplitude, that means oscillations are dying out, okay, with time. Okay, so this can be written you know, this can be expressed in the form of you know, harmonic function. I will show you this later. Okay, but before that we will discuss 4 cases. Case 1, if beta is equal to 0, beta is equal to 0 means there is no resistance. That means this term occurs due to damping. Okay, that means there is no damp. Okay, this is simple harmonic oscillation. That means there is no you know, resistive force like friction or air resistance. Okay, so then we're gonna left with you know, only this term as well, which gives the oscillation. Okay, then the graph of oscillation will be like this, sinusoidal maybe, or okay, or cosine graph. Okay, and in this case number 2, beta square minus omega naught square. Okay, this one, if beta square is minus omega naught square, in that case this part will be imaginary. Okay, and here you see, here when we had beta is equal to 0, then here we had got e to the power 0, which gives 1. So then we will left with this part only. Okay, but now beta is not equal to 0. Okay, when this part is missing, then you can say the oscillation is simple harmonic. Okay, but with this term, the oscillation is dying with time, like this. Okay, this is damped oscillation, right? It is dying with time, so it is called underdamping. This is called underdamping. Underdamping. Okay, now case 3. Okay, when this beta is equal to minus omega naught, beta square is equal to omega naught, then here we will get e to the power 0, here also we will get e to the power 0. We end up getting only constant e to the power minus beta t into c1 plus c2, that's gonna be constant. So if this part is constant, it doesn't mean oscillation. Okay, so its graph should be something like this. Okay, initially it has displacement, there must be displacement initially, but it dies with time, like this. Okay, and there will be no oscillation, and because of this term we will get this graph. Okay, so hope you have understood this. I will show the graph at the end. Okay, and this is called critical damping. And case 4, when beta square is greater than omega naught square, okay, then it is called overdamping. Because you see, when beta is greater than omega naught, then the power on this E, that will be a real number. If the power is real, in that case this e to the power this root over beta square minus omega naught square, that's gonna be a constant. Okay, in that case also when e to the power beta square minus omega naught, if this power on E is real, in that case we will not get the harmonic function. Okay, and then if we don't get that function, then we will get no oscillation. Okay, so when we get imaginary, suppose e to the power ix, that gives cos x plus I sin x. So when you get cos x sin x, this is a harmonic functions. Okay, so then you will get the oscillating effect. Okay, right? Hope you have understood this. Now you see, let me take this solution and let me copy this solution and let me go to the new slide. Okay, so here is the solution. Now you see, let's do one thing. Let us take minus common from these two. Okay, you see, root over beta square minus omega naught square. If you take minus sign common, it can be written this way. Okay, right? And because of minus 1, we can consider I square. Okay, and which can be written as I root over omega naught square minus beta square, right? So that's why we can write this solution in this way, that e to the power minus beta t is into c1 e to the power I root over beta, instead of beta square now we're going to write omega naught square minus beta square into t, right, plus c2 e to the power again minus I root over omega naught square beta square t, right? That's how we can write. Now you see, as we know that e to the power I x is equal to cos x plus I sin x. If we apply this identity here and here, okay, when you see, then what you're gonna have, let me show you. So now you see, we're gonna apply this formula, okay. So then x of t is equal to e to the power minus beta t, then within bracket we can write c1, okay, let me write here square bracket, okay, c1 cos, instead of x we have root over omega naught square minus beta into t, okay, plus I sin root over omega naught square minus beta square into t, okay. And similarly, if we apply this one here, this formula, okay, then what we're gonna have, plus c1, sorry, not c1, c2. So here this minus will be plus, that's gonna be that's the only difference, okay. So let me copy this above result. So we're gonna end up getting this result here. This minus sign will be, this plus sign will be minus, okay. So that's what we're gonna have, right? Hope you have understood this, okay. When you put here minus, this should be minus, okay. So now you see, let me simplify this. Here you see, from these two terms we can take this part common, okay. Then within bracket we're gonna have c1 plus c2, right? So that means e to the power minus beta t cos root over omega naught square minus beta square into t, and within bracket we're gonna have c1 plus c2. So on the other side, on the other hand, here you see, if you take this two common, then you're gonna end up getting c1 minus c2 because there is minus sign, okay. Hope you have understood this. I sin root over omega naught square minus beta square into t, and within bracket we're gonna have c1 minus c2, okay. So hope you have understood this. That's what we're gonna have, right? Now let me copy this result and let me take a new slide, okay. Just give me a second. So here is the last step we have got. Now let us replace this by a and this by b, okay. So we can write this way actually. We can write c1 c2 first, then we can write this. Similarly, we can write this one first, sorry, right, like this. So now let us consider that this is x of t. Let us say c1 plus c2 is equal to, suppose, capital A, and c1 plus, sorry, not plus, minus c2 is, suppose, capital B, okay, is, suppose, capital B. So then this above equation can be written in this form. Just give me a second. So let us replace c1 by c2 by a, capital A, right? And let me replace this I c1 minus c2, okay, I c1 minus c2 by capital B, okay. So hope you have understood this, okay. That's how we have written. Now let's do one thing. Let us consider that A is equal to, capital A is equal to small a sine phi, okay, sine phi, and capital B is equal to small a cos phi. Okay, if we assume that, then we can have, so we're going to replace this a by sine phi, we're going to replace this b by small a cos phi, right? Then this equation will take this form. Just give me a second. So then here you see, so let me replace the a and b. Okay, let me replace a and b by those values we have considered. Okay. So a is replaced by small a sine phi and b is replaced by small a cos phi. Okay, now here it is in this form: sine a cos b, cos a sine b, there is sine a plus b. In this form, sine a cos b plus cos a sine b. If we apply that formula, then it can be written in this way. So let me copy this step and let me take a new slide. Okay, so here is the last step we have got. Okay, now here this small a is taken common. Suppose this can be written here. Just give me a second. So a is taken common, right? So let me rearrange all these things. Okay, we can write this way. Now you see, it can be written this way: a e to the power minus beta. Using the trigonometric identity, we can write this sine root over omega naught square minus beta plus sorry, I forgot the t, plus phi. Okay, sine a plus b formula. Now you see here, this part, this is x of t. Here this root over omega naught square minus beta square, this is, let it be omega. This is omega. This is the frequency of damped oscillator. Okay, this is the frequency of damped oscillator. So here we can write this solution in this form. Just give me a second. So we can write this, we can replace this root over omega naught square beta square by omega. So now here you see, this is the harmonic function, right? And here this small a is the initial amplitude. Okay. Initial amplitude. Okay, hope you have understood this. And this frequency, this is actually angular frequency. It also can be written in this way: omega is equal to root over omega naught is, you know, k by m. Omega naught square is k by m minus beta square can be written this way. We have got beta is equal to what? We had considered b by m twice m, not m. So beta square will be b by 4m square. We can write this way: b square by 4m square. So this is the angular frequency, right? And therefore frequency of damped oscillator, so this is the angular frequency of damped oscillator. Okay, so this is the angular frequency. Let me write, this is the angular frequency of the damped oscillator. sorry, just let me write this way. So give me a second. This is angular frequency of the damped oscillator, right? Angular frequency of damped oscillator. Therefore, frequency of damped oscillator nu will be equal to, we know nu is equal to omega by 2 pi. So that's why we can write the, so let me mention this amplitude here. Okay. So frequency of damped oscillator, can be written this way. Just give me a second. That will be nu is equal to omega by 2 pi. So which means 1 by 2 pi root over k by m minus b square by 4 m square. This is the frequency, right? And if you need to find a time period, let me take a new slide. Let me copy this expression we have got. Okay, time period t, we know that omega is equal to 2 pi by capital T, right? So t will be equal to 2 pi by omega, and 2 pi omega is equal to this. So let me copy this expression and write here. So this is the time period. Here you can see these are the graph for case 2, 3. This is for case 2 under damping. This is for critical damping, case 3, and this is for case 4 over damping. Okay, and if you consider the case 1, that when beta is equal to 0, then you will get simple harmonic graph like this. Okay, then oscillation will not die out for beta is equal to 0, right? Hope you have understood this. So thank you for watching. See you in the next video. Bye bye, take care.